A mountain in the Washington Cascades is doing something mountains should never do. It's sliding downhill, too slowly for your senses to detect, but fast enough that USGS GPS receivers track every millimeter of its movement. This ridge, let's call it Sawtooth Ridge, a nickname already adopted by several local geologists, forms part of a remote slope scientists have been monitoring since 2015. And it's drifting about 4 inches every year, nearly 4 feet per decade. If this entire block ever breaks loose, it could trigger a landslide larger than anything in recorded U.S. history. Before we go deeper, what do you think is driving this slow collapse? A. Water infiltration. B. Earthquake activity. C. Something geologists didn't expect? Drop your guess in the comments, because the answer is buried far below the surface. You can see the motion if you know where to look. Halfway up the slope stands a lodgepole pine, its trunk bent roughly 15 degrees downslope, the uphill roots exposed above the soil like a hand slowly losing its grip. A few meters away sits a brass USGS survey marker hammered into bedrock in 2010. When researchers returned in 2023, they found it 53 inches downhill from where it was originally mapped. Yet hiking here feels completely normal. The forest is silent. The ground is firm. Your eyes insist everything is stable, while the data insists the mountain is slipping away beneath your feet. And the movement isn't random. The entire slope behaves like a geological ratchet. Every winter thaw, every rainfall spike, every seasonal swell pushes it forward by fractions of an inch. Each cycle loosens the slope's grip just a little more. USGS teams tracking the ridge, measuring displacement every 6 months, have confirmed the detail that keeps them up at night. The movement is accelerating. Because the real force behind this drift isn't above ground. It's a hidden clay layer, roughly 300 feet deep, formed at the end of the last ice age. And it's finally waking up. When geologists finally drilled into the slope beneath Sawtooth Ridge, they found something they had suspected for years, but had never been able to confirm. A buried, water-sensitive clay layer roughly 300 feet below the surface. Likely a bentonite-rich remnant, formed as glaciers retreated at the end of the last ice age. This layer forms the shear plain, the geological fault line on which the entire block of land is slipping. It behaves almost nothing like the rock and soil above it. Most of the Cascades are made of rugged, fractured volcanic material, sharp, angular grains that lock together like broken glass. But bentonite clay? It swells, softens, and loses friction the moment water enters it. And that's the real danger. Every seasonal moisture cycle, snowmelt in spring, autumn rainstorms, midwinter thaws, pushes more water down into this buried layer. Over hundreds of cycles, this clay transformed from a stiff, compacted material into something closer to a slick, deforming pad that can shear under the weight of an entire mountainside. Geologists mapped the slip boundary and found the plain tilting slightly outward, like a broad, shallow ramp angled toward the valley. Not steep, not dramatic, but smooth enough that once the clay weakens, the entire ridge behaves like a geological conveyor belt, creeping forward millimeter by millimeter. And here's the number that made researchers go still. When the clay reaches 18% water content, its strength collapses, dropping by more than half. Sawtooth Ridge has begun touching that threshold more and more during the last decade. That's where the science becomes terrifyingly clear. As water saturates the bentonite layer, pore pressure spikes, the force of water trapped between tiny mineral grains. This pressure acts like a hydraulic jack, lifting the overlying rock mass ever so slightly. When pore pressure rises, friction disappears. When friction disappears, the entire slope can begin to float on its own lubricated foundation. That's the moment when a slow slide can turn into an unstoppable one. And here's your checkpoint before we move on. Which factor do you think increases pore pressure fastest on this ridge? A. Rapid snowmelt. B. Prolonged rainfall. C. Blocked subsurface drainage channels. Drop your answer in the comments. Because the true trigger isn't just water, it's the timing of it. And that timing becomes critical in next section. If the clay layer 300 feet below Sawtooth Ridge is the buried fuse, then the sensors pinned across the slope are the ticking clock. For nearly a decade, the mountain's drift followed a predictable rhythm. 4 inches a year, slow, steady, almost polite. But starting in 2021, the numbers broke from that pattern. The drift didn't just continue. It began to accelerate. And geologists know that when a slow-moving slide speeds up, it often means one thing. The slope is entering the dangerous transition from secondary creep toward tertiary creep, the runaway phase, where collapse becomes inevitable. Scientists aren't watching one metric. They're watching 3, each more alarming than the last. First, GPS displacement. Ground-based receivers and satellite-linked telemetry are tracking motion down to the millimeter. Those once stable velocity lines now bend upward, responding sharply to storms, snowmelt, and rapid thaw cycles. Each event injects water into the bentonite-rich clay layer below, raising pore pressure, the internal water force that pushes grains apart and strips away friction. When pore pressure rises fast enough, the rock mass begins to behave as though it's floating. That's the signature of a slope inching toward loss of control. Second, LiDAR and drone imaging. Repeated scans are revealing a widening, horseshoe-shaped headscarp at the ridge crest, a fracture large enough to swallow saplings. New tension cracks are radiating outward along the flanks, marking the exact boundaries of the block that's detaching from the mountain. These are not surface-level scars. They're the geometric outlines of an emerging failure plane. Third, the invisible clock. Geologists are plotting the mountain's inverse velocity, a forecasting tool where the trend line doesn't lie. When that curve bends toward zero, velocity trends toward infinity. That's not metaphor. That's physics. And Sawtooth Ridge's line is now curving in exactly the wrong direction. Which signal worries you most? A. Accelerating GPS. B. Growing headscarp. C. Bending inverse velocity curve. Tell me your pick, because the deadliest trigger rarely looks like the scariest one. Add these signals together, and Sawtooth Ridge is no longer a passive hazard. It's an active countdown. All it needs is a catalyst, a 100-year rainstorm, a rapid snowmelt pulse, or even a minor regional tremor. When that moment arrives, the timeline won't stretch across years anymore. It will compress into minutes, and that's when the real disaster begins. When Sawtooth Ridge finally fails, it will not look like Hollywood. There is no warning roar, no cinematic cracking. The shift begins with a deep, subaudible flex along the buried clay plain, the same weak layer that's been degrading for thousands of years. And when that boundary gives way, the entire 1.2-mile block moves as one coherent mass. At first, the motion looks almost gentle, a few inches, then a few feet. But within seconds, the slide accelerates past 10 feet per second, and in some modeled pathways, even faster. Once a rigid slab of rock and soil reaches that threshold, there is no realistic way to stop it. This is a runaway failure, the mechanical equivalent of a locked brake suddenly releasing on a slope. As the upper ridge collapses, the crest drops roughly 150 feet, instantly converting gravitational potential into kinetic energy. Hundreds of millions of cubic yards of material surge downslope, enough to bury a downtown district under a 200-300-foot thick layer of shattered earth. This is the primary slide zone, short range, annihilating anything close to the source. But the catastrophe doesn't end there. Beneath the main block, the collapsing mass pulverizes into a debris flow, a fast-moving, liquid-like slurry. This secondary hazard races down the valley floor at high speed, sweeping up timber, boulders, soil, and anything in its path. It can travel miles beyond the initial impact zone, channeling into river corridors where downstream communities and infrastructure become vulnerable. And then comes the most counterintuitive danger of all, the air blast. A slide of this scale displaces such an enormous volume of air that it generates a shock front capable of snapping mature trees before the debris even arrives. Numerical simulations show how the air column can compress and race outward faster than the slide itself. It's why some geologists, informally, refer to these rare, high-energy failures as megablast slides. If you were standing several miles away, which hazard reaches you first? A. The main slide. B. The debris surge. C. The air blast. Drop your guess, because the real answer is the least intuitive one. And here's what makes it even more unsettling. The direction of failure determines everything. One trajectory points into uninhabited forest. Another lines up with a river corridor and communities downstream. The mountain already knows which way it wants to fall, but that direction is still shifting, inch by inch. If previous sections answer the what, Section 5 answers the who. Because once a slide of this scale begins to move, it's not just the mountain that changes, it's the map. And here's the part most people don't realize. The exposed area is not a circle. It's a corridor, long, narrow, and brutally directional. The danger follows the valley the slide chooses. Sawtooth Ridge sits above a small, steep drainage that funnels everything, blocks, mud, air, down a single chute. If the failure initiates toward the northwest flank, the slide runs into uninhabited forest. That's the best-case scenario. Millions of tons of displaced earth, but minimal human exposure. But if the block fails toward the south or southeast, that's where the stakes rise, fast. Within minutes, the primary slide would enter a narrow valley that feeds directly into a river corridor lined with recreation sites, seasonal cabins, and two-lane access roads. None of these areas are designed for a mega-slide scale impact. Bridges? Vulnerable. Campgrounds? Exposed. Roads? Potentially buried under tens of feet of debris flow. and downstream communities, miles away, face a different hazard. Not direct impact, but water displacement. A slide dropping into a river doesn't just block water, it forces it upward and outward. Think of a sudden rise in river level, surging downstream in a pulse that acts less like a flood and more like a moving wall of brown, debris-filled water. But here's the counterintuitive part. The air blast could travel even farther than the debris. A large enough failure could send a pulse of compressed air racing several miles down valley, toppling trees and hammering structures that never see a single rock. This means the risk profile changes depending on where you are. Within 1 mile, primary slide impact. 1 to 3 miles, debris surge plus channelized flow. 3 to 6 miles, air blast plus water displacement effects. Beyond 6 miles, infrastructure ripple effects, roads, power, communication lines. Let's do a quick reality check for attention. If you live in a small river town downstream of Sawtooth Ridge, which threat would you worry about most? A. Direct debris. B. Air blast. C. Sudden river surge. D. Losing access roads and infrastructure. Drop your choice, because Section 6 will show how fast emergency planners say you would have to react. When a slope the size of Sawtooth Ridge collapses, the event itself lasts minutes, but the consequences reshape an entire region for centuries. Landslides this large don't simply bury valleys, they redraw them. The first change arrives instantly, a newly formed natural dam. Hundreds of millions of cubic yards of rock and pulverized earth would slam into the valley floor and choke the river corridor, creating an abrupt, towering blockage. Within hours, water begins backing up behind it, forming a lake that could stretch miles upstream. Some dams like this last decades, some fail within days. Either outcome transforms the hydrology of the region overnight. Downriver communities face a different threat: sediment shock. A slide of this size injects an entire hillside's worth of fine material into the watershed. Turbidity skyrockets. Fish habitat collapses. Channels shift. Flood risk increases for years to come as the river struggles to flush the new load downstream. Meanwhile, on the mountainside itself, the slide scar becomes a raw, open amphitheater of exposed bedrock. A cross-section of the mountain's interior revealed in an instant. Vegetation won't return quickly. It takes decades for soil to rebuild on a surface like this. The landscape enters a new ecological clock cycle that won't mature in a human lifetime. But the most dramatic transformation isn't physical, it's cultural. Communities that once treated the Cascades as permanent, immutable landmarks now have to confront an uncomfortable truth. These mountains are not frozen monuments. They are active systems, still adjusting from the last ice age, still shifting under seasonal stress, still capable of sudden, region-scale change. And that brings us to the real question, the one geologists quietly debate every time a slow-moving slope begins to speed up. If a slide like this is a once-in-a-millennium event, how many other ridges are quietly preparing for their turn? Before we wrap up, which long-term impact hits hardest for you? A. River damming. B. Sediment shock. C. Permanent landscape change. Drop your answer, because the Cascade's next chapter is already being written.